The first key term we're going to be using a lot with cells. Again, when I say cells, think of batteries which powering your phone, or think of a double or triple A battery. You've got a bump on the top for one of the terminals. You've got the bottom of a battery that is the other terminal. They say plus and minuses to them. When we make voltaic cells, we're going to have pieces of metal that are going to act as that positive and negative piece of a battery. Okay. Now, the connection where oxidation is occurring is defined as an anode. Okay, now these are terms you don't use when you use batteries. You just think, oh, there's a plus and a minus. You don't worry about how they use. But one of those terminals on a battery is referred to as an anode. And we'll eventually connect the battery terminology you're used to with our cells. Okay, there's a lot of vocabulary in this unit. In the previous unit and in this one, we had oxidation, we had reduction, we had OAs, we had RAs. Now that we're doing cells, anode and cathode are two key definitions. When you can figure out which of the electrodes, okay, which metal end has oxidation, you found the anode. Where reduction occurs is where the cathode is going to be. Now the agents work, they're the opposite terms, okay? And I use agents a lot. When we use our redox table, the first column is all oxidizing agents and the second column is all reducing agents. So if we use that vocabulary, okay, what's on the board is the definition, but connecting to the table, okay, where oxidation occurs, that's going to be where we're going to find the reducing agent. Okay, kind of the opposite word. So the anode is where the RA will be located or reacting. The cathode is where reduction occurs, so that's the oxidizing agent. Okay? So something from the first column is going to be reacting at the cathode. Something from the second column in your table will be reacting at the anode. Okay? Next two definitions you know already, just reinforcing them. We're going to have ion movement to balance charge, so I'll be using the term anode a lot. Or sorry, anions. Okay? We're going to see negative ions moving in our solution, and we're going to see positive ions, cations, moving in solution. So that's just a recap. Okay? Next key term is a salt bridge. In making a cell, a chemical cell, you have to have a complete loop. Okay? We're going to be making two half cells, and then we got to connect them. One of the connections will be with electrical wires. The second part of the connection is going to be with a salt bridge. Okay? And the salt bridge is where we have these cations and anions moving. Okay? Last key definition, and this one is a reminder, just about the term electrolyte. We have to have solutions that are electrolytes. We have to have conductive solutions with ions, or our cells don't work or batteries don't work. If you take a whole bunch of negative charge out of a battery, okay, electrons flowing out of a battery, that part of the battery will become positive and it will kill the battery unless you have ions flowing in to replace that negative. Okay? So every time a unit of electrons comes out of the battery, a unit of anions has to move over and replace where the electrons left to keep it neutral. So we need conductive solutions. We need salt bridges to help ions moving from one part of a battery to another, or one part of a voltaic cell to another. Okay, so let's jump in. Some of these terms are a bit hard to understand, like salt bridge. You need to actually see it. So let's look at an example of what a voltaic cell is going to look like. So this is something I'd like you to write into your notes. It's something I'd like you to write fairly big, because I'm going to label, well, which one is the anode? Which one is the cathode? Where do electrons flow? Okay, this is like a battery. Electrons need to flow. Cations, where do they move? Anions, where do they move? So I'm going to start going through this voltaic cell and understanding it and doing all that labeling that I mentioned. Okay. The first thing, before I do any labeling, I have to understand the chemistry. So I'm going to figure out what is the oxidizing agent, what's the reducing agent. So I'm going to pre-set up OA, RA. We're going to find out in our second lesson today, there's a reason I'm always putting the OA on the top and the RA on the bottom. It helps us predict the voltage later. Right now it doesn't matter, but this is the pattern I want you to get used to. So what is the strongest oxidizing agent in this setup? Voltaic cells have to have both sides of a half reaction. If you look at the blue one, that's got copper metal as the electrode. It just says copper electrode. The word copper would be just a neutral metal. And there's copper 2+ ion, okay? And I've labeled on a data table that half reaction, okay? And we've got both sides, okay? And again, that's always true in voltaic cells. It's part of the definition of a voltaic cell. So our blue beaker is this top sort of red box, both sides. The zinc beaker has zinc metal as the electrode, and it has zinc 2+ ions in it. That's this bottom red box. And again, we have both sides. Now, we don't need to go and write out a big list. Whatever half reaction is higher up will always have the best OA, because the best oxidizing agent is the one that's higher up in the first column. So our strongest OA, okay, is going to be copper 2+. Okay? Our strongest OA is in this beaker. This is the beaker that has the oxidizing agent. So I'm going to write out that half reaction, and then we'll go back to the previous slide and figure out, is the OA next to the cathode or the anode? Our oxidizing agent is going to be copper 2+. That's going to gain 2 electrons and make more copper neutral metal. Let's find the reducing agent. Okay. The reducing agent is always from the half reaction that's lower down, okay? Because the strongest RA is lower down in the second column. So there's our strongest reducing agent. There's our strongest oxidizing agents. Voltaic cells always have both sides of half reactions, and they'll always have an OA above an RA. They're always spontaneous. Okay? You never have a voltaic cell that doesn't run. Okay? So there's our strongest RA. That's the zinc metal. I have to write the reducing agent half reaction in the reverse of your table. Now, in a second, you can do this ahead of me. That oxidizing agent, that copper 2+, this beaker, we're about to find out which electrode it is. So the oxidizing agent, where reduction occurs, is the cathode. Okay, reduction, OA, that's referred to as the cathode. Okay, and you'll be asked to identify cathodes. So I just went -C as the cathode. Okay. Now the cathode has to be a physical piece of metal, okay, that you could actually like connect your circuit to. Okay. So in this voltaic cell that I'm about to build on the bench and the one you have in your notes, this piece of metal is our cathode. Okay. So I'm going to label that. So our zinc metal must be the anode. Okay. The zinc is where oxidation is going to occur, or the RA. If we think of what's going to happen at the cathode is what? Gaining electrons. Okay. They're pulling them in. Okay. The anode, the reducing agent that has the anode, is going to be where the zinc is reacting, and that's spitting out electrons. Let's find that anode. The RA is at the anode. The anode is spitting out electrons. Anode, RA, electrons are coming out. Electrons are going to be coming out of this anode from the zinc metal. What do you think the easiest path is going to be to get to the other side? Go through all this water or go through this electrical wire? The wire is going to have low resistance. The electrons are going to go from the anode, and they're going to go over to the cathode. And that pattern is always true. The electron motion is always anode to cathode. So if we kind of think of what's going on here, I'm not going to scroll down, but you've got the reactants at the anode, the very bottom of your page. Zinc metal is the reactant. So this anode is actually reacting away. This anode is going to get smaller and smaller and smaller over time. Okay? One of the products is 2 electrons. They're going to go through the wire. There's less resistance. Okay? The other product is what? Zinc 2+. That was the other product. And that's going to be coming. The zinc metal is going to react, and it's going to stick zinc 2+ into the solution. That's where the other product's going to go. And we're going to talk about ion movement in a little bit. We're going to have positive charges building up in this beaker, which will kill our battery unless we neutralize them. Let's flip over to the other cell. Okay. Electrons are coming here. What's the reactant and product? So look at that oxidizing agent at the cathode. It's copper 2+. Okay. So it's not the copper metal. It's not the actual electrode this time. It's copper 2+ in the solution is going to the electrode and becoming more electrode. So this copper electrode is going to get a little bigger and bigger and bigger over time. So the electrons are going to come down through the wire, through the electrode, where the electrons and the copper 2+ meet, will make more solid copper. Okay? I'm not going to write the Cu. I'm just going to try to show this electrode getting bigger. No, copper is actually brown, but I'm making it black. None of this works without a complete circuit. Okay? And that's what the salt bridge does, is it links the 2 pieces of the cell and allows ion movement. Now you can memorize the pattern or you can just figure it out. Okay, we're figuring it out. We're getting a whole bunch of positive charges formed here. We need to neutralize them, so we need anions. I'm just going to go A for anions. Doesn't matter what it is. Something negative has to come from the salt bridge and neutralize that zinc 2+. Now to remember this pattern, I just remember double vowel, anions to anode. It's always that way. Anions always flow towards the anode. Cations always flow towards the cathode. They're now replacing positive charges in this example. Copper 2+ is being neutralized. Every time a copper 2+ is neutralized, some cations come out of the salt bridge and replace those 2 charges that were removed. So cations to cathode, C to C. Anions always move to anode, A to A. So that's your patterns. At the end of this lesson, I have a nice summary page that repeats all these patterns for you. One last little bit, I sometimes forget to, I don't mention this very much, so make sure you don't forget this. You'll sometimes see internal and external cell, particularly on diplomas. The external cell is just the wire. So everything above that blue line is the external cell. The internal cell is all the wires, the chemistry, the electrodes. The electrons flow through the external cell. Now, I did want to add in the polarity, the positive and negative terminals. Now, it's always going to be the same pattern. Okay? The negative terminal is going to be where the negative species is going into the wire. So your anode is always the negative terminal. And when you use a battery, the negative terminal is where the electrons are coming out of. The electrons go through the wire or through your phone or through the light bulb, and they go to the cathode, which is positive. On your multimeter, the red is the positive, the black is the negative. So that's how you have to hook this up. So the positive terminal is going to go to the cathode, the negative terminal to the anode. If you do it backwards, the voltmeter will give you a negative number. It shouldn't be there. You get a negative number in the lab, you have your cell, you've got your wires backwards. It doesn't hurt anything, it doesn't break anything. It's just hooked up wrong. Okay. Next is we need some short forms. If I want to tell you about a cell, I can't draw all this out. It's too much. We need a way to convey this beaker and that beaker really quickly. And that is done using cell notation, and you need to be able to decode cell notation. Okay. And we're going to write an example of cell notation once we're done explaining and learning about it. The blue box is the actual cell notation. All the arrows and labeling outside the blue box are all the patterns that are always true. Okay. The cell notation starts with whatever the anode is. This has to be a solid. It's a negative terminal of your cell. Okay. Then you put a vertical line, and then you put any of the electrolytes or anything other than the anode. In the example where you've worked through, the anode was the zinc. Okay. It doesn't matter which way the drawing you have in front of you is positioned, you must start with the anode. Okay. When you do a drawing, you can draw it any way you want. Anode on the right, anode on the left. Okay. The double line is telling the reader we're switching half cells now. We're leaving behind this clear zinc beaker and we're switching over to the blue copper one. Okay. We're going to start with the electrolyte or everything other than the cathode first. Okay. So you'll notice you'll have a double line and you see the electrolytes on each side of it. You see another single vertical line, and that separates the writing of the solid cathode. Okay. The actual piece of metal, that is the positive terminal of the cell. Okay. So we've got a bunch of patterns written around it. You don't have to write all the patterns down, but you need to know them all. Maybe you put them on the cell before. Okay. Hopefully you know it's that anode to cathode is the electron path. Okay. It was from the zinc over to the copper electrode. Okay. Oxidation always occurs at the anode. Reduction always occurs at the cathode. Okay. No exceptions. Okay. The cation and anion movement, that's the same letter to same letter. The cations always move towards the cathode, C to C. The anions, which start with an A, always move towards the anode. So that's why I remember that. I'm going to write out the cell notation for the example that we just did. I'm going to lay out those dashed lines first. So we have to have the anode electrolyte, a double line to switch beakers, electrolyte, and then last the cathode. You may want to be flipping back to the diagram as I'm writing this in. Okay? I have to start with the anode. Okay? The solid anode is the zinc metal, and it actually was one of our reactants. Then I move to anything that's in this solution. Zinc nitrate. Nitrate's a spectator ion. It didn't show up in our chemistry. Sometimes you'll see the spectator ions left out or put in. Okay? If I ask you to do cell notation, you don't have to put in the nitrate, but you do have to put in the chemicals that react. Now we have a double line, and now I've got to express what's going on in this half cell. Okay. It's got copper nitrate, aqueous. That's the blue solution, very dark blue solution. Last, I end with the cathode. That's the positive terminal, this actual piece of metal, and it is copper metal. And that's my cell notation. A nice fast way that I can talk about a cell. I can give you notation and ask you what's the anode or the cathode, or later I'll ask you what the voltage is of the cell. It's quick and efficient. Next bit that rolls out of a problem we're going to run into, writing cell notation or building a cell, is you must have a solid for your electrodes. Okay? When you look through your table, okay, Voltaic cells are built from having both sides of a half reaction. Now, right off the bat, the very first half reaction, I've got a problem trying to make a half cell out of it. I've got fluorine gas and fluoride. I have no solid. Okay? So we're going to need something to act as that terminal, the actual positive terminal of the battery or the negative terminal if there's no solids in the half reaction. Okay? So we're going to add in an electrode, but we call it an inert electrode. Okay? It's not an OA, it's not an RA, it's just something to act as where you attach the positive or negative wire to. There are two examples of inert electrodes that you will see in this course. The first is a carbon inert electrode, a graphite rod. The other really common inert electrode that you'll see on test quizzes, homework, is platinum. There's no platinum as an OA or an RA. And it's a good electrical conductor. So platinum, solid. Where you'll see this in cell notation is maybe I have the 0 voltage half cell. Right in the middle, the hydrogen-based one, H plus and hydrogen gas. Okay. If I wanted to use that half cell, I'm going to have hydrogen gas. Okay. So I'm going to need a tube or something to trap hydrogen gas, and I'm going to have H plus ions in solution. But there's nothing to act as my electrical connection. So I'm going to have to pick something like platinum to act as I've written this as if it's going to be a cathode in this particular layout. When you're doing a homework question and you see platinum or carbon here, you know it's not the OA or the RA. You've got to go looking here to see the pieces of your half cell. So we've got carbon, we've got some iron ions, we've got some dichromate and H+, another carbon electrode, and I am going to draw the cell. I'm going to label the pieces of the cell. Now when you're done writing, you'd want to have your redox table out in the class. On blue, I have boxed out the two half reactions that I see the pieces based on this question. Okay. Now cell notation makes our life even easier. I really don't even need to go and try to find OAs and RAs. I need to realize the format of cell notation. When we write half reactions, again, I'm always writing the OA first, which now I'm going to add -C because that's at the cathode. Which side is the cathode? It's got to be over here. This side has to have the reaction at the cathode. Okay. The actual cathode is going to be carbon. That's an inert electrode, so that's now my chemistry. The strongest OA is, well, there's dichromate and H+. Dichromate H+, there's my oxidizing agent. Okay, I didn't even look at the iron. Okay, that has to be at the anode. My table is going to tell me my reaction at the cathode. So it's dichromate, 14H+, 6 electrons. So if I want to understand what is my reducing agent, which is going to occur at the anode, now I only want to look here. I've got carbon, that's inert. Oh, I don't really care about that. I know that's not my OA or RA. I've got a Fe2+ or 3+. One of those has to be my reducing agent, and it's got to be the second column. So there's 3+, 2+. It's got to be the 2+, has to be the reducing agent. So the 2+ turns into the 3+ and 1 electron. So Fe2+ goes backwards to 3+ and produces an electron. So I wrote out the half reactions. I'm going to skip doing the net. You've seen me net up 2 reactions before. I want to spend my time drawing the cell. but I wanted to highlight how you can get the two half reactions really quickly from cell notation. So I'm going to start labeling a bunch of pieces. I know I need 2 beakers. Okay, so those will be our 2 beakers. I'm going to label a salt bridge right away. You're always going to need a salt. Okay. Sodium nitrate is the one that I used, and if you want to memorize one salt, memorize sodium nitrate. So that's going to be in our salt bridge. Okay. If we don't have a salt, it doesn't work. If I put like methanol or ethanol or some molecule in there that isn't an electrolyte, our cell doesn't work. It's useless. I put a wave to be the top of my solution in each beaker. I've labeled 2 electrodes. When I look up, well, that's a carbon electrode, so I'll label that one as carbon. The other one is actually a carbon electrode too. In solution, we've Fe2 plus and Fe3 plus. I'm leaving out the aqueous because I don't have a lot of room to write. In our other beaker, we have dichromate, Cr2O7 minus, and H plus. I'm going to need an external cell, so I have to connect a wire from one electrode to the other. And now I'm looking at the part B, all the things the question asked me to draw. So draw a cell labeling the electrodes. So I put what material they are. I'm going to put which one is which. Okay. The dichromate half cell has to be the one that has the cathode. The iron 2 plus 3 plus, that beaker has the metal. That's going to be the anode. I'll do the polarity right away. The anode is negative. That's where electrons come from. E minus is going to flow from the anode to the cathode, which is our positive electrode. In terms of ion movement, I don't have to analyze the cell. I could just use memory. Cations go to cathode. So that would be the sodium plus is going to be heading towards the cathode. The nitrate, NO3 minus, that's an anion, and that's going to move towards the anode. It's always that pattern. So the word standard has a very particular meaning in chemistry. Standard tells us that we must have all the components of the 2 sides of a half cell. Okay? You'll see that word in lots of questions. It leads to a short form. It's not mentioned here. If you're told you have a standard copper cell, it's telling you it's got both sides. It doesn't just mean the copper metal, it means the ion and the metal. So that's one way that it's used. Okay, so that's part of the definition. Another part is a standard cell is always 1 mole per liter. And only under 1 mole per liter are these values true. Okay, standard is summarized in this little knot symbol or this little circle. Okay, that's standard state. Okay, it's something you've seen before. Okay, and what we're leading into today is standard potential. Now, potential difference is often called voltage. Okay? Standard cell, if you ever get a test question, what's the standard cell potential? I'm asking you, what's the voltage? Is it 1 volt, 2 volts, 1.5 volt? Okay. Okay. E naught cell is the term we're going to use for standard cell potential. The E naught cell is, again, so many volts. Okay. It's the maximum electrical potential difference between 2 half cells. It kind of tells us how much oomph does each electron have as it goes from one side to the other. The higher the voltage, the more energy an electron delivers as it goes from one side to another. You can think of voltage as being how steep is the hill. Low voltage would be a very gradual hill. When something falls down a gradual hill, it doesn't have as much kinetic energy as it falls. A really steep hill, more kinetic energy because it's going to fall faster. So what we're going to, next we're going to run into, well, where do these numbers come from? How did, where does this 2.87 volts come from? And we're going to start with, why on earth is this 0? Okay. You wouldn't think any of the half reactions would be 0, and it's not 0. We defined it as 0. Okay. The standard hydrogen half cell, so we see this word standard, so meaning everything in the hydrogen half reaction is present. On my table in class, I'll grab, chemists decided that that half cell is going to be our 0 volt reference. Okay? We can't measure the voltage of half a cell. Okay? In order for a battery to work, you have to have the whole loop. So there's no way to measure just one half. Okay? So this 0 was picked, okay? And then everything is relative to hydrogen. Take our hydrogen cell, we're going to pair up our fluorine fluoride cell to it, and whatever we measure on our voltmeter for this other cell, we're going to put in the table. Okay. The hydrogen cell was left, our first half cell, the next half reaction standard cell was made up, paired up with our 0. Whatever we measured, we put here. All of these numbers are what you get if you build a cell with hydrogen and the other cell, and all of the number was applied to the other cell. Okay. So this 0 is picked as a reference. Okay. Scientists do this all the time. 0 degrees Celsius doesn't mean 0 temperature. We just picked it as a reference. Okay. You can go above 0 or below 0 when you just pick an arbitrary reference, and that was done here. Okay. Now this works because what we ultimately are going to care about is what's the voltage difference. We're going to be comparing one cell to another, and the difference in voltage between my hands, it doesn't matter what my reference is picked. We're always going to get the same difference between one number and another number regardless of what we picked as our 0. Okay? There's always going to be a certain voltage difference between two cells. Okay? So the main message from this slide is the 0 was picked and everything is relative to hydrogen. Okay? Relative to hydrogen, fluorine is a better oxidizing agent. We get a positive number. Okay? If you take the hydrogen half cell and you compare it to sodium, sodium is a much worse OA. We get a negative voltage compared to hydrogen. Everything's in reference to hydrogen. Okay? The big thing we need to be able to do is get the differences. So we're finally going to calculate voltages. So what do we do with the two numbers in the table? To get the E0 cell, which is our voltage, we've got to look up the E0 reduction. Okay, well that is this. This is a reduction table. Okay, the E0 voltage are these numbers. Okay, we've got to take the E0 cell at the cathode, which is going to be our OA, and I've been training you all course to write OA first, RA second. It's because of this slide. You're going to take the reduction potential of the oxidizing agent, the higher one up, first, and you're going to subtract the E0 reduction, the value right in the table of the anode one. Okay. So if you take the way you've been writing equations, take the top one minus the bottom one, take the OA at the cathode minus the RA at the anode. That difference is your E0 cell. So we'll do one example of this. Okay, we just got to figure out our chemistry first. Okay, so I'm going to determine the half reactions, which we've done before, and do the standard cell potential for the first time of the following cell, and I use cell notation to describe it to you. So I'm going OA dash cathode, because the oxidizing agent, which is going to have the reduction, which occurs at the cathode. The RA, which will have the oxidation half reaction, occurs at the anode. You should be pleased when you see cell notation on a test, because if you know the patterns, it saves you lots of time. You have to have the anode first. You have to have the cathode second. If it's not in that format, it's wrong. It's inappropriate. It shouldn't be done. So I want to get my oxidizing agent and the half reaction for that reduction first. That'll be at my cathode. So only looking for my OA on the cathode side, the second half of our cell notation. I see carbon. Oh, that's an inert electrode. So I'm not looking there. I'm looking for chromium 2+, 3+ in my table. And that's going to have the strongest OA. So where do I find chromium 2+, 3+? There's chromium 2+, 3+. So the one that's going to be in the first column is going to be the OA. The first column is the OA. The second column is the RA. So there it's at minus 0.4 something. And the first one is the oxidizing agent. So chromium 3+ plus 1 electron gives me chromium 2+. And now I'm going to write the E0 potential for the first time. Make sure I've minus 0.41 volts. Switch now to my anode. That's got to come first in cell notation. So I'm looking for either iron metal or iron 2+. And I'm very biased. I know neutral metals are always reducing agents. I probably know what it is right away. That half reaction better be lower down, and it's the one right below it. Now the reducing agent is always in the second column. So it's iron going backwards. So we've got Fe solid producing Fe 2+ plus 2 electrons. Okay. And now I'm going to write its electric potential difference, or this reduction electric potential difference, and that's minus 0.45. The voltage of the cell is a subtraction of the cathode reduction potential minus the anode. So if you write this the way I've set it up, cathode first, anode second, all you need to do is subtract those numbers, take the red, which is minus, subtract the black, which is minus, and you'll get the cell potential. Okay? The standard cell potential if you had 1 mole per liter of all of these aqueous chemicals. And that is a positive. You better get a positive value if it's voltaic, or you've flipped something or done something in reverse. 0.04 volts. Not going to be a very good battery for us. You're not going to run much on 40 millivolts, but that is the potential difference of this cell. Okay. This is something you may or may not need to add to your notes, but it's a nice condensed key for everything today. So I would make your own version of this or copy this down. So voltaic cells are always split in 2 pieces. You've got that LEO, okay? What's losing electrons oxidized, that's going to be your RA, that's going to occur at your anode, and that's negative. The GER, your OA, is going to be the cathode, and that's always positive. Okay? that electron flow I talked about a few times, it's always the negative anode to the positive cathode. It's always A to C. Okay. Ion movement is A to A, anions to anode, cations to cathode. The salt bridge needs to have a salt, but it can't be the best OA or RA in your reaction. It needs to be spectator ions. So you're seeing a different example here of a good salt choice, sodium chloride. A poor OA paired with a poor RA. Use an inert electrode if a half reaction does not have any solids that can act as a natural electrode.